Find the value of k such that these two vectors are perpendicular. For this, we can use the dot or scalar product. So a dotted with b is the magnitude of a times the magnitude of b times by cos of the angle in between them. So if they're perpendicular, the angle in between them is going to be 90 degrees. Cos 90 is 0, so the dot product is 0. And that brings us to the next version of the dot product, which you can show is just the x components of the vector multiplied together plus the y components plus the z components. And that means we're going to do 1, 2, 1, dotted with minus 2, 3k, times the x components to give minus 2, times the y components to give plus 6, plus k, that's going to equal 0. That's 4 plus k is equal to 0, so k is going to be minus 4. Next up, we've got two lines with equations written in vector form, and we're asked to find the point of intersection. Now, just a reminder, we start at the origin, and this vector gets us onto the line. So it's our position vector to get onto the line. And then the other vector is the direction vector, because it tells you how far you're going to go. Well, actually, it tells you the direction you're going to go, and then lambda tells us like what multiple we're then going, and that will give you the vector, and it will always give you the one on the line, a vector that leads you to a point on the line. So if we want to find a point of intersection, we basically want to get the same coordinates at the end, or the same position vector overall, and therefore what we do is we set the components equal to one another. It must be that 3 plus lambda, that's the x component for L1, is equal to 6 plus 2 lambda, the x component of the vector L2. And then 2 minus lambda is going to equal 5 plus mu. I'll write the third one down in a minute. Actually, I've got enough information to be able to solve this, and it's quite nicely set up. I can just add them together, these two equations. That will leave me with 5 equals 11 plus 3 mu. So 3 mu will equal minus 6, mu will equal minus 2. I can sub that back in. I mean, I've got enough now to find the point of intersection, but I think it's good to just check that the third equation is consistent. So I'm going to sub it back in, and that means that 2 minus lambda will equal 3, so lambda will equal minus 1. If I now write down my third equation, I just need to check that it is okay. So I get 7 plus 3 lambda is equal to 2 minus mu. And if I sub in, then I would get 4 equals 4. So it's all good, basically. And now I can either sub mu in or lambda into my equation. I'll put it into this one, I think. So where they're going to intersect, it's going to be r equals 6 by 2. And now I can replace mu by minus 2. So I'll multiply the vector, this direction vector, by minus 2 to give me minus 4, minus 2, 2, which gives me 2, 3, 4. So the point of intersection is then going to be the coordinate 2, 3, 4. On to the very last part, we're told that the vector 1AB is perpendicular to the lines L1 and L2. What that actually means is it's going to be perpendicular to the direction vectors of the lines. So this one here and this one here. Because remember I said we get onto the line using the first vector, and then we go along some multiple of these direction vectors. There's a couple of ways we can do this. The way that jumped out at me was to do a very similar thing to part 1. Okay, let's just take the dot product of this vector with the direction vectors one at a time. So it must be that 1AB dotted with 1 minus 1, 3 is equal to 0, just like before. And that means 1 minus A plus 3B is going to equal 0. Or maybe I'll rewrite it as A minus 3B equals 1. And then 1AB dotted with the other direction vector 2 1 minus 1 is also equal to 0, which means 2 plus a minus b is equal to 0, or minus a plus b is equal to 2. I can add these two together. I've got simultaneous equations. That will leave me with minus 2b. If you want to add them, the a's cancel. Minus 3b plus b is minus 2b, and I'm going to get 3. Therefore, b is equal to minus 3 over 2, or 1.5. I can put that back in, put it back into this one. So that means that a is going to equal a is going to equal b minus 2, which means it's minus 1.5 minus 2, that's minus 3.5, or minus 7 over 2. I've left it as fractions, but minus 3.5 is fine as well. So those are our two answers. Now there is one other way you could do this question. I personally think the scalar products and simultaneous equations is probably the easiest, but we could instead find because it could be another time we're asked for this, find the equation of a line that is perpendicular to two lines. You actually take the vector product. So what we can do is to get a vector that's perpendicular to L1 and to L2, then we take 1, minus 1, 3, and we put a little times, or sometimes you see it written like this. Maybe I'll go with the times. A different type of vector multiplication. And without really going into loads of details, it can be shown that this can be written as a determinant with I, J, K on the top, and then 1, minus 1, 3, 2, 1, minus 1. So now we figured this out by expanding along this row. So I'm going to get I times the determinant of minus 1, 3, 1, minus 1. Okay, I just take the I and then I look at this bit here. This one's positive, by the way, because it's the first row, first column, it's minus 1 to the power of 2. But the next one becomes minus j, because that is the first row, second column, so it's minus 1 to the power of 3. It's important to get that in there. And then, like, you just cross these out. That's what I did before, really. So 1, 3, 2, minus 1. And then back to plus k, because it's minus 1 to the power of 1 plus 3. And then cross out this, and we get 1, minus 1, 2, 1. Okay, I've not left enough room. I'm just going to bring it down to the bottom. So now we can expand each of these determinants. So I'll get 1 minus 3. That will give me minus 2i. Minus j, then it's minus 1, minus 6. So that'll be a minus 7. So actually I'll get plus 7. And then with the k, I'll get 1 minus minus 2. I'm going to get 3. K, which I can write as the vector minus 2, 7, 3. And that vector must be a multiple. I was about to use k then, but I probably shouldn't because I've got k as my vector. So maybe lambda multiplied by 1ab. Remember, we're told that 1ab is perpendicular to both. This vector, by construction, is perpendicular to both. It's just, it's a scalar multiple of the 1ab. Now we can see that lambda is going to have to equal minus 2. That is the only way I can multiply it by 1 to get minus 2. So that means it's going to equal lambda minus 2a minus 2b. So 7 is equal to minus 2a. A is equal to minus 7 over 2, just like before. And 3 is equal to minus 2b. B is equal to minus 3 over 2. It's worth, like, even if you think scalar products is simpler, which I think it is here, remember to practice the vector product for other instances. gives us the same answer. So nice to see. Well done on this question.